Mungana 40.
Anyone who is able to hear anything? Can't get anything.
Okay. Good afternoon, Mr. Meet. Hello.
Mr. Hamwin. Mr. Hamwin, are you there? Hello?
Hello?
Mr. Hamwin.
Hello, I'm here.
There now. Okay, good afternoon.
Hello.
Hello.
Good afternoon, sir.
Come to Gwasha Wadara, Jaji Tajin Trade.
I'm here. Good afternoon. I'm here. Good afternoon.
Hello.
I don't think there is anyone who is hearing what is lecturing. No. Just seeing the pictures.
His
He hasn't
microphone
yet
is not
started.
picking anything. His microphone is not picking anything. So if he's talking, then the microphone is not functioning. I suggest we restart the meeting. I suggest we restart the meeting.
We can even hear Stephen. Meeting.
Merera Jakapantambo. Hello, are people able to get me now?
Yes.
Yes,
Hello?
sir. Hello,
Yes.
We can get you now.
No.
Okay. Sorry for that. My mic was not well connected.
No, it's fine, sir. Thank you.
Okay, so I will just start from the beginning. So I was saying that at the end of this lecture today, we are dealing with water flow in pipes in open channels. So at the end of it all, I should expect you to understand the different concepts that are related to open channel flow, and in the end, we should be able to design an efficient system which is going to deliver water to our farm without or with minor losses. So previously we've been talking about water flow in pipes, and today we are switching it to open channels. You notice that there are a lot of similarities between these two, but one difference that we'll notice is that water in open channels is usually under it's exposed to the atmosphere. So we find that the channel is usually open and it's exposed to the atmosphere. Unlike pipes, where it's a enclosed conduit, where water is just within the pipe and is not exposed to the atmosphere unless where it's coming out from. Now this exposure to the atmosphere now will make a life a bit complicated for us, because it will give us problems when we're solving computations to design open channels, because in open channels we find that the water depth maybe will be differing at different points, and maybe the land is not very flat and things like that. So it will create a bit of problems, but with efficient computations and considerations, we should be able to get around that without any much difficulties. So when it comes to open channel, there's three factors which usually affect the flow of water in the open channels. So the first one is the geometry of the channel itself. So the geometry of the channel, which is the shape basically. So this would determine how much water you can transfer in that channel. So the bigger the channel, the more water you can transfer through it. So there are usually two things that when we talk of geometry, that we are looking at. One, we are looking at the area, the surface area, and as well as the perimeter. So we are looking at these two because we can have the area of the channel, but it's not always that channel is going to be full. So instead of us just using the area as we did for pipes, we're going to introduce another parameter, which is the perimeter. So the perimeter is simply the area which is weighted by the water. So if you can have a bigger area, but the amount of water in that area, in that passing through that channel, is less. So when doing your computation, you won't use the actual area because it's not full. So instead, we combine it with the perimeter, which shows how the amount of area which is occupied by the water. So usually what we do, we combine these two parameters, the area, which is the full potential, then the perimeter, which is the area which is occupied by the water now. So we come up with another parameter which we call the hydraulic radius. So this is simply the ratio between the area and the perimeter. So now this is what we'll be using in our computations for designing open channels. So this has an implication on the volume of water which will pass through that channel. The next factor is the slope. Of course, we we talked about it in the previous lectures. So the steeper the slope, the more water, the higher the speed the water can travel. So because now we are dealing with open channels, usually we are dealing with natural movement of water. So you need to create a slope which is going to drive the water. So if your slope is steep, the rate of water moving will be higher than when you have a flat surface. Then again, just like pipes, the roughness of the surface in the channel is going to inhibit how fast the water moves. So the roughness of the channel is another factor that we should consider when we are designing the channels. If it's rough, you expect that water will move at a lesser speed, and also there'll be a lot of friction. So these are the three factors that we will consider when designing our channels. So now, if we look at the geometry of these channels, unlike pipes, which were almost every time cylindrical, for open channels, they can take different shapes. They can be rectangular, you can make it a semicircle or different shapes. Others can be triangular, others like a trapezium, and things like that. So this will have an effect on how you calculate your area and how you calculate your perimeter. So this slide here shows the different formulas for different shapes of channels. That's for area and for perimeter. So depending on which shape you want to use, these are the formulas that you can use to determine the perimeter and the area. So just take note that not all open channels will have the same formula for area and perimeter. So they will have different formulas depending on the shape. So now if we have these open channels, you remember that our goal is to deliver a certain amount of water to our field, which is basically the discharge. So in designing these channels, we need to calculate the velocity of the speed at which water should travel in that channel for us to achieve a certain discharge. So the design of an open channel is mainly to determine the shape of, not necessarily the shape, but how deep and how wide your channel should be. So it's basically determining the geometry of your open channel. So to determine this, to determine the flow of the velocity of water in our channels, there are different formulas that are given, but almost all of them are dependent on three things. So it's going to depend on your hydraulic radius. So the hydraulic radius is a parameter which is affected by the area and the perimeter. Then it also be affected by the slope and roughness. So these three things are common in all these equations here, the four equations that we can use to determine the flow velocity in our channels. So the first one we can look at is the Manning's equation, this one here. So it has four variables. So the S is the slope. Then the the C is representing the roughness of the channel, and the R is the hydraulic radius. So this R is a factor which is affected by your area and your perimeter, while this K here is a parameter that is affected by the material that you are going to use. For example, if you are in a sandy soil or you are in a clay soil, this factor will differ. So if you have these facts, all these, then when you multiply all of them, it will give you the velocity. It will give you the rate at which water will be traveling in that channel per unit time. So again here, you notice that the K, as I said, it's due to the soil. So this one will be tabulated in tables, and it will be always given for a particular soil, as well as this C, which stands for the roughness of the channel. So this will also be a factor that has been determined for different materials, for clay soils, for sandy soils, and other types of soils. So the K and the C are empirical and have been tabulated. So in our design, the only thing that we are looking for is the hydraulic radius as well as the slope. These are two things that we need to determine as we are designing our channels. Then we move to the Chesney equation. It's also basically using the slope and the radius, while the K, as I said, is given for every soil, as well as the N. So in this one, instead of using the C, they've used N. It's also a coefficient which has to do with the roughness of the material that has been used. Then we have the Hazel-Williams equation. It has similar parameters. So it has the C, the R, and the S. So it just depends on which one is appropriate for you to use at that particular time. Another one which is closely related to the Manning's equation is the Darcy-Warbeck equation. You can see that this and this are similar, only that now it has introduced these two powers on the R and on the S, but everything works the same. So you can choose which one equation to use depending on the circumstance in which you are in. So depending on which parameters you have been given, but all of them will work in the same way. So using these equations, you can determine how fast water can move in your channel based on your slope and based on your hydraulic radius, as well as the roughness of your material. So this table just shows the different coefficients that I talked about. So these are different materials that can be used to line your drains, and it has these coefficients N for different materials. You also have the C coefficients for different materials, as well as the K values for different materials. So using this, now you can be able to fix them in the equations and then be able to calculate the flow rate. So for different materials, different soils, there are recommended slopes that you can use, or else when you go beyond those slopes, the velocity of the water will increase to the effect that it will start eroding your channels. So experimentally, they've done a lot of research to to say, okay, if you're in a sandy soil, you should not exceed this slope. If you're in a clay soil, you can go up to this slope. As well as the velocity itself. A lot of experiments have been done to show the limits to which water can move in a channel that is on a certain type of soil. So you don't want to exceed that velocity because it will start to drain, it start to erode your open channel. So these things, we take them into consideration when you're designing your open channel. So we'll look at this when we look at an example of how now we can incorporate these permissible velocity, slopes, and the other parameters in designing an open channel. The other thing that I would want to make mention is that for energy, the energy concept that we talked about in pipes, it also applies in a similar way to open channels. It's just the same principle as we did in the previous chapter. So we won't dwell much on this one because it's the same principles applying. So now, since we've seen those factors that affect flow in open channels, we're just going to go through a simple procedure which we can use when we're designing an open channel. So remember that when we're designing an open channel, the thing that we want is to have the geometry. We need to get it right on the geometry, mean that the shape of the channel, so that we deliver the right amount of water to our farm. Then also we need to know what materials to use to line our channel so that we reduce on the friction that is occurring on the surface. So basically, designing open channels is more on the geometry. So if we are given we come into we are given a job to say, okay, we need to design a channel that is going to take water to a farm. These are some of the steps that we can use to achieve that objective. First of all, we need to know the material where we're going to work on. Is it a sandy soil? Is it a clay soil? Is it rocky? Is it what kind of material is there? Such that once you know that material, you can easily determine some of the parameters, like the N, which has to do with the roughness of the material. Then we also have the slope, the permissible slope, which is given for every material, as well as the permissible velocity. So these ones, you get them from literature, the tables that we had. For example, if I go back here, you can easily get the slope here, the suggested slope for different materials, as well as the velocities. Then you can also get these coefficients for different materials that you're going to use for lining your channel. So once we have these, now the second thing that we need to determine is the hydraulic radius. Now we know that the hydraulic radius is what determines the area and the perimeter. So since we have determined the velocity from the permissible velocity from the first step, we can use the Chesney formula, which we gave previously. So it means that using this Chesney formula, you have your velocity, the permissible velocity, your N, which you get from tables, as well as your K, as well as the slope, the permissible slope. So the only thing which you'll be missing now is this R, which you can solve because you have everything else. So the R is the only thing which is missing. So you can solve for it by making it the subject of the formula. So once you solve for your R, which is your hydraulic radius, you can also solve for your area, because you know that you need to deliver a certain amount of water, which is the discharge. And when you divide discharge by the velocity, the permissible velocity which you have, you get your area. So you have two things that you have determined here. You have your hydraulic radius and you have your area. And we know that hydraulic radius is the ratio of the area and the parameter. So using these two, the hydraulic radius and the area that you get, you can compute your perimeter using this equation. Now you have both the area and the perimeter. So now the question is to find out how deep should be your drain and how wide should your drain be. So we know that from the formula of area, we have two things that are which you multiply. So you have your length and your breadth. So you need to find, so this length is like the height of your drain, or the depth of your drain, and this breadth is how wide it is. So these two are also found in the formula for perimeter. So since you have the value for your area and you have your value for your perimeter, you can solve these two equations simultaneously using simultaneous equations. And one thing you can do is that from this one, you can make L the subject of the formula. And then once you do that, you replace it into the perimeter formula. And once you do that, the only unknown that you have will be your breadth, which is how wide your channel is. And when you solve for this one, you can now go back and replace it here and then find the depth of your channel. So using that, now you're able to know, okay, my channel should be this deep and it should be this wide for me to deliver this amount of water to my farm. So this is basically how you come up with the geometry of your open drain. But we'll go through an example at the end so that we appreciate this phenomenon. So after we have done that, we've known the dimensions. We need to make sure that the amount of water that is delivered through that system is we don't lose water. So we need to be efficient. So the amount of water that enters our system should be equal to the amount of water that leaves our system. So in this case, we need to make sure that we reduce on the losses. So in most times, the loss is usually associated with evaporation and seepage, but evaporation is usually very low. So one thing that we need to consider a lot is the seepage, the downward movement of water from your channel into the soil. So we need to make sure that we avoid losses due to seepage. So to do that, we need to make sure that water is not infiltrating from the base of the channel into the soil. So one way in which we can do that is by lining our channel. So we can either plaster the channel or put a layer of concrete on our channel. Others put a plastic. Others put different types of materials to line the channel. Others do it by compacting. They compact the soil in the channel so that there are less holes which water can penetrate through. Then others use chemical substances like sodium salts. They just apply them through the channels. These sodium salts will make the soil to become to disperse, and once it disperses, it will block the openings that are there in the channel, and water will find it difficult to go below that soil. So these are the three ways in which you can reduce seepage and make sure that the amount of water that you are putting into your system is equal to the amount of water that is coming out at the end of the drain. Yeah, so that's for the efficiency of open channels. You want it to deliver enough water. You don't want to have to incur a lot of losses. So the next thing that we'll look at now is what we call hydraulic structures. Once you have done your open channels, there are other things that you need to do to make sure that your channels are working efficiently. One thing that you need to do is that you'd want to control your discharge, because now open channels, water will just be flowing through. But you need to have control to say, okay, when I irrigate for this amount of time, I need to close, for example, the channel so that water does not go into my field, or else you're going to have a flood. So there are hydraulic structures that are used to do that. Yeah. So I think that the meeting was going to close in a few seconds. So once it closes, you can just rejoin again using the same link. So maybe I'll just wait because it's less than a minute. I'll just wait. I'll just take a break of maybe 2 minutes so that when it stops, people can rejoin. Then we'll continue on this section of hydraulic structures. So as we are waiting, if there are any people who have questions, you can just bring them through so that as we.
Yes, Mr. Miti.
Yes.
This is Mrenga Stephen.
Okay.
Yes. I want to say we appreciate the way the flow of things are going.
Okay. Thank you very much.
But maybe just to add on,
okay,
it would be appreciated if at all you had come up with some examples, especially on these same formulas that are interlinked.
Yeah.
Yeah, it will be very much appreciated because it will be easier when you're seeing the workouts. It will be easier to assimilate the messages.
Okay. Okay. Yeah. That's very important. So what I've done at the end of this slide, we'll look at one example, but as well, I'm compiling different scenarios and of problems which you might encounter and how you can solve them. So maybe by the end of tomorrow, okay, let me just say by the end of the week, I should be able to give you a PDF document which has questions and answers on how you can solve such kind of problems.
That would be very much appreciated.
That would be very much good.
Yeah. So yeah. So you just make sure that you understand the scenario, because once you go in the field, you're going to face different scenarios. It won't be like exact as we are doing it here. But so I'll try and give different scenarios, then you'll be able to follow through on how we can solve it. But if yeah, but if as well you can organize yourself at some point, if you need any assistance, you can as well just do another meeting, another Zoom meeting anytime outside outside this schedule which we have this week, so that we go through whatever problem that you're going to find. Okay. Yeah. Yeah. So I think we have most of the people back in the meeting. So I think we can proceed from here. So we're talking about hydraulic structures in channels, and we said that when we do channels, we need to now regulate. If the water is passing through my channel, I need to regulate how much of that water is going into my field, or else in the end I might have a flood. Or if the water where it's coming from, there's a flood, for example, upland. So it means that water will be coming very fast in my channel. And if I don't protect it, it might get eroded. So there are certain structures that I can put in my channel to avoid such kind of scenarios from occurring. So there are different structures that we can put up to control the water levels and discharge in our channels. One of them is what we call a weir. So it's represented in this picture. Once you go to your module, you'll be able to see it clearly, and then there's the explanation of how it works. So, but basically, what it does is that you put, if you have a channel, at some point you block it. You block it so that you don't block it until the whole height of your channel, but maybe until half. So eventually what you want is that for water to come to the other end of your channel, the other side should be full, or it should first disperse water in the first part of your channel. Then when it gets full, up to that level which you have blocked, for example, you see here. So this channel is maybe until down there, but now it has been blocked with this V. So for water to go through, it needs to fill the first part. Then it will come this side. So that's one way of controlling the level of water in your drain. Then the other way that you can do is that you can make what we call a sluice gate. So if this is your open channel, what you do is that you, at the point where you have a channel which goes to your field now. So this is an open channel coming from your source. Then at some point, it needs to branch so that it goes to your field. Maybe you have 5 fields. So the first branch goes to field 1, the second branch goes to field 2, and the third to field 3. So what you do is that you block your channel. Instead of making it big, you use something that you're going to be sliding. For example, you slide it to open and you slide it to close, in such a way that if you want to stop irrigating in that field, you simply slide it and then it closes that channel, and the water will now proceed in the other direction to go and water the second field. And if your second field is done, you close as well until all your fields are irrigated. So we call that a sluice gate. When you get to your module, you'll be able to see exactly how it works. But basically, it's just a gate which you close and open. Then we say that sometimes you might want to regulate the water, because if, for example, you have a flood upland, it means that water will be coming with a higher force into your channels from upland, and if you don't regulate it, it might cause it might erode your channel. So what effectively you want to do is that you want to reduce the energy with which water is coming into your field or your channels. So one way you can do that is by creating step structures in your channel. So if after a certain number of meters, you just create a small step going down, so that as the water is coming, as it is dropping on that step, some of the energy is being lost as it is hitting down the step. So some of the energy is being lost as it is hitting down the step. And if there are a lot of steps that you have created, it means that the water energy will be continuously reducing, and you save your channel from being eroded. But also, instead of putting step down structures, you can put up step up structures, so that as the water is coming, for example, this is the step up structure. As the water is coming this side with a lot of energy, once it reaches this obstacle, some of the energy will be dissipated here. And now as it goes this side, it will be a bit slower. Or if you want, you can even just put stones in your channel, which will basically just act as barriers to water. If it's coming at a high speed, it's hammering into those stones. The speed at which it's moving will be reduced, and in the end, you save your channels from being eroded. So that's another way of using structures to protect your channels from getting eroded. So we've covered the process which is required for us to design a channel. Then we've gone further to say, okay, if we design a channel, we need to make sure that we have efficiency. We don't lose water as we are delivering it through these channels. So in that case, we put lining, or we compact, or we use chemical substances. Then now here we're talking about how to control the discharge in the open channels. So now I want us to, maybe in the next 5 minutes, we just go through we just go through an example of how we can go about this phenomenon of designing an open channel.
Twarira tatushimwa.
Yeah, so there's someone who's on the phone. Let me see if I can mute him. Okay. Okay. So we'll just go through one example on how to design. Then with the other examples that I'm going to share with you, you should be able to go through and see how best you can design a channel. So I'll stop sharing this screen and I'll share a new one, which is an example of how we can design an open channel. So given an example that we are tasked to design a channel that will carry this amount of water. So we want to be delivering 6.91 meter cubic of water per second to our farm. And we've gone to survey the farm and we've realized that the soils there are clay soils. And okay, we say, okay, we're going to use a slope of 0.00318. Yeah, so now we'll go through that procedure of determining the shape of that channel, how deep that channel should be, and how wide that channel should be for us to deliver this amount of water to your farm. So we know we've been given the discharge, or we've determined the discharge, and we know the slope of the land itself. So now again, when we surveyed, we saw that it was a clay soil. So we go into those tables which we saw in the PowerPoint, and then we check what is the N value for the clay. We find 0.025. Then we also go to the suggested slope in those tables. Okay, they say, okay, it's 1:1 is good. Then again, we go to the velocity table and it tells us that, okay, 1.8 meters per second is the maximum velocity that you can apply to this soil. Or else, if you apply a higher velocity, it's going to erode your soil. So we have these parameters that we have checked from literature and others which we have seen from our survey. So as we said, when we're designing an open channel, what we want is to find the depth and the width. And this can be found from the area. If we know the area, then we're able to know that, okay, this area is the height times the width, or the depth times the width. So we know that discharge is equal to area times velocity. Now we've been given the discharge, okay, and we have determined the velocity, the permissible velocity. So using these two, using discharge and velocity, we're able to find the area using the equation which says discharge is equal to velocity times area. So you see here, this is a typo error. This A here is supposed to be V. Okay, so just take note. So this is V, the velocity. So area will be equal to discharge over the velocity. And once we compute that, we'll find that the area should be 3.83 meters. So we have achieved one objective. We found that the area should be this amount. Then from the Manning's equations, those equations that we saw, the different equations in our PowerPoint, the ones we use to determine the velocity, you can pick whichever is okay for you, depending on where you are. Then we saw that in that formula, in those formulas, there was the velocity, there was the n value, and there was the slope, and there was another value, the hydraulic radius. Okay, so the velocity you have, the n you have, the s, which is the slope you have. Now the only thing that you miss in that equation is the r, which is the hydraulic radius. So when you make it the subject of the formula and you solve for it, in this case it's not shown here, but when you solve for r, you find that you get 0.713 meters. Now again, we know that this r is the ratio of the area and the perimeter. So now we have the value for r and we have the value for area, meaning that we can determine the perimeter by simply dividing the area by the hydraulic radius. Then we get our perimeter. So we have determined the area and we have determined the perimeter. So once we have these two values, it will be easy for us now to know, to determine the height and the width of our drain. So you remember we said that the area and the perimeter are not the same for all shapes. So what you do, you go to the shape that you want to use, and then check the formula of how to determine that area or perimeter. So in this case, when we check that table which had the different, let me just stop sharing this one and then I show you what I'm talking about. So if we go to this table, we see that there are different ways. If your channel is rectangular, or if it's triangular or a trapezium. So you choose which formula to use. So in our case, these are the two formulas. So this is for the perimeter and this is for the area. So in these ones now, we have these two equations. We can solve them simultaneously. And in the end, when you solve them, you can make either B or Y the subject of the formula and then fit it into the next equation. Then you solve for the unknown. So in this case, you're going to have your Y, which is our depth, equal to 1.222 meters. And now since you have your depth, which is your Y, you can just place it here and then find your breadth, which is your width. But once you find your depth, you can just have an allowance. You can add an allowance of maybe 2 meters, just to make sure that your drains do not overflow. So just put a small allowance to allow for overflow. Then once you have that, it means that you have your depth and you have your width of your channel. So basically, this is how you can be able to design a channel. Then once you do this now, you now make sure that you line it to avoid seepage of water. So yeah, this is an example of how you can use those equations that we saw to do this, to solve this problem. So I'll prepare different scenarios, then I'll send for you to go through them. Then I also make an assignment for you just to appreciate how these things can be done, and just to see how well you've understood the concepts. So if I send these examples as well as the assignment, just make sure you read through those and make sure you understand, because your assessment will be almost similar to these kind of examples. So your exam will be most likely similar to this. It won't go further from what we have covered. So if you're not clear anywhere, you can either send a WhatsApp, or you can send an email, so that we go through them so that you understand. So I think for today we'll end here. I think you have another class that you need to go to. So I think I'll just end here for today. Then tomorrow we'll look at drainage, so that on Friday we'll just look at different questions. I'll just be going through different questions on how we can solve hydraulic problems. So I think I'll end here for now.
Thank you.
Thank you, sir.
All right, thank you.